In this video, we're going to work through part number 3, the third and final review, while preparing for the first test of our trigonometry course. We'll begin this review like we have the others on the no calculator portion of the test review. In this particular problem, we're being asked to determine the 6 trigonometric functions based on the triangle below, and we will report our answers in fractions. So the 6 trig functions are listed here, and you should recall that they are simply ratios of side lengths. When we're talking about the sine trig function, we need the opposite side length to be divided by the hypotenuse. For cosine, we want the adjacent side length to be divided by the hypotenuse. And for the tangent ratio, we need the opposite side length divided by the adjacent side length. And our reciprocal functions on the right side are easy to obtain. We simply flip the fractions for the first from the first 3. And that's it. This question asks us for the trigonometric functions, or the values of these functions, not the value of theta itself. So these answers are good. Question 2 asks us to draw a right triangle with sine theta equals 8/17, and then find the remaining 5 trigonometric functions. So this question is real similar to the first one, except we are asking you to actually draw a triangle that fits this description. And this diagram does not have to be perfect, but it should be characteristically similar. Since the sine function requires the opposite side length to be divided by the hypotenuse, we want to try to draw this opposite side length that's relatively, I should say sized relatively correct to the hypotenuse. This isn't perfect, but it's pretty close. That way, when we compute our third side length, which is necessary to determine our remaining trig functions, the result that we get for this side length should seem reasonable. We can use a Pythagorean equation here because this is a right triangle and we're missing one side out of 3. And if this side length computes to 15, I think this diagram is pretty reasonable. And now that we have a completed triangle, we can answer the remaining trig function values just like we've done before. And those answers seem reasonable to me. There are a couple different ways you can approach a problem like number 3. In each case, we're being asked to evaluate the inverse of sine, cosine, and tangent at a particular value. What I would encourage you to recall is that any trigonometric function that's written, sine, cosine, tangent, or secant, cosecant, or cotangent, generally require a theta value to be provided, and the end result ends up being some sort of trig ratio. That's the general pattern for any of our trigonometric functions. But if we're involving an inverse trig function, then we provide the ratio and expect a result that is an angle measure. So that's what's happening here. We're providing the ratios inside the argument, and then the end result is supposed to be an angle measure. So if your brain works well enough backwards, then just simply think of these questions that way and produce a result. You can find, for example, the positions inside of a unit circle where an angle will produce a sine result that's equal to -1. Another way to think of this is to rewrite this problem as a traditional trigonometric function, sine theta equals -1. And that too reminds you to look for the position inside the angle measure where sine is equal to, the position inside the unit circle where sine is equal to -1. In either case, I would consider a unit circle first and try to find the position where the y-coordinate is equal to -1. I know it's the y-coordinate because we're dealing with a sine function, and the sine function determines our y-coordinates. This occurs at precisely 270 degrees, and only 270 degrees. The instructions don't specify, but you could also report your answer in radians, or you may be asked to report your result in radians. 3 pi over 2 is the same position. In part B, we're thinking, where does cosine equal -1/2? Cosine inverse of 1/2 implies that we would like to know which angle measure applied to cosine produces a result of negative 1/2. Well, again, considering a unit circle, where in this unit circle are the x values equal to negative 1/2? Well, that occurs here and here. So theta must be 120 degrees, or theta must be 240 degrees. When reported in radians, we would report this as 2 pi divided by 3 radians, or 4 pi divided by 3 radians. And again, these answers come to me quickly because I have the unit circle memorized, and you should too. In part C, we would like to know when does the tangent of an angle measure equal the opposite of the square root of 3 over 3? What would be helpful to note here is that the rationalized result, negative radical 3 over 3, is the same as negative 1 divided by radical 3. And if we write the fraction negative 1 over radical 3, we might recognize that that was obtained by taking the fraction 1/2 and dividing it by radical 3 over 2. We'll use the negative symbol here. That chain is helpful to recognize because the tangent function is described as our y-coordinates divided by our x-coordinates. And now when we consider our unit circle, we can find the position where y is 1/2 and x is radical 3 over 2. Now the end result has to be negative, so we want either a negative 1/2 divided by a positive radical 3 over 2, or we can accept a positive 1/2 divided by a negative radical 3 over 2. In either case, we're referencing this position. Y value is a positive 1/2, while an x value is negative radical 3 over 2. Or this position. Y value is negative 1/2, while the x value is positive radical 3 over 2. So the position in degrees would be 150 degrees or 330 degrees. The position in radians would be 5 pi divided by 6, or 11 pi divided by 6. Since the question didn't specify to answer in degrees or radians, then either solution would be accepted. If the instructions do specify, then you must report in that result, or in that form. If you can't answer in that particular form but choose to answer in the other form, partial credit will be awarded. As far as the unit circle goes, I've just jumped to a different section in our notes. You should be able to complete this, filling in all angle measures in terms of degrees, radians, and coordinates in under 5 minutes. I've asked you to practice these on your own and time yourself outside of class. And if you've been keeping up with that, then this section of the test should be no problem. Additionally, you should be able to identify where trigonometric functions are positive, and the format goes like this. All are positive in the first quadrant, sine is positive in the second, tangent is positive in the third, cosine is positive in the fourth. All students take calculus was the phrase that we used to memorize that one. So if you're given this entire sheet on the calculus test, on the trig test, you should be able to do just fine with that. I may ask you, in the interest of time, just to complete a quarter of it or a half of it or something like that too. So in either event, you should be prepared to handle that. Now we've seen questions like this in our review prior, so I'm going to ask that you pause the video now and try this one on your own. You can reference, I think it was review number 2 for the techniques that we use to solve it. Using sine and cosine appropriately, we can identify the coordinates, and identifying equivalent angles that produce the same cosine, sine, and tangent values are a matter of locating the appropriate position inside the unit circle. 50 degrees off of horizontal for this example, 40 degrees off of vertical, and either 50 degrees off of horizontal or 40 degrees off of vertical to identify the tangent result. In question number 7, we're being asked to find all angles between 0 and 360 degrees that satisfy this equation. Now let's keep in mind that if cosine of some unknown value is equal to negative 0.1, then x by itself would be equal to cosine inverse of 0.1. And this is a calculator permitted portion of the test. So punching this expression into the calculator would be fine. However, the calculator will only give us one solution. So cosine inverse of 0.1, correction, that should be negative 0.1, produces a result of 95.7392. So x is equal to 95.7392 degrees. But we need to pause here for just a second because that's not the only solution. This position, 95.7392, is located right here. And so we've got a data point at this position. Where else inside the unit circle does the cosine equal the value associated with this angle? Well, that would be in the other position where the x value is the same. So down below we have the same x value, and this position also has the same cosine result. Now there are a variety of ways that we can identify this new position. For me, I recognize that this position that we just computed is 5.7392 units past 90 degrees. So therefore the result down here is going to be the same number of units, 7392, before 270 degrees. So this angle measure at this position is just before we get to 270, and that result computes to 264.2608. And we can check this result as well. If I enter cosine inverse of 264.2608, sorry, that's not correct. I did not mean to use the cosine there. What we're checking is to see if cosine of 264 will equal the negative 0.1 that we're after. So I should use cosine, not cosine inverse. We always supply an angle measure into the trigonometric function, not a ratio. So 264 is the angle measure. And when we evaluate cosine at this angle measure, we do get negative 0.1. Rounding error, of course, because we rounded our result before. So I'm satisfied with these two results. Again, only one came from the calculator originally, but the other was easy to compute. In problem 8, we're going to do the same thing, only this time we're being told to find the answer in radians. So all angle measures in radians. So we want to use cotangent inverse of 0.25. That will produce the theta value that we're after. So the calculator must be changed to radians. Let's do that by simply clicking the phrase up here. If it says DEG, you click on the screen and it'll switch to radians. That's sufficient for the change. We'll select inverse cotangent, and enter 0.25. So that's 1.3258 radians. 1.3258 radians. Now it's not immediately clear where that sits in the unit circle, but certainly you can figure this out. Since this second position is pi radians away, we can simply add pi to this value. And with this calculator, we can take our previous result, add to it pi. We have a key for that. And press enter, and our new radian angle measure is 4.4674. 4.4674 radians. And I would be satisfied with those two results. Again, we've got to be careful here because the calculator in either of these two examples will give us only one result, and we must know what to do to find the other, or at least determine our way through that. For question 9, we're solving the entire triangle. Find the unknown side and angles in this triangle. This one happens to be a side angle side triangle, so the law of cosines would be the correct method to use to start this process. Remember that after we use the law of cosines at least once, we could potentially switch to another law or another method for finding components, but most certainly we'll use the law of cosines, at least at the beginning. So here's a list of the provided information, and certainly by now you should have had enough practice to know that side length b is easy to compute at this point. In fact, many of you will have this form of the law of cosines memorized. This expression here will isolate the value b, lowercase b that is, for the side length. And from the calculator I see that this result is 8.7034 units. Now for me, I recognize that these two measurements that are diagonal from one another would be sufficient for us to change to the law of sines to solve for angle A or angle C. So here's the expression set up, and what I'd like to point out is that we're rounding our result from before to 4 decimal places, and we may lose some accuracy. If you're concerned about precision in a problem like this, you can actually write the entire expression that was used to calculate b from before inside of this expression, and there would be no loss in accuracy. The TI calculators will store this value. Well, I guess there will be some loss of accuracy. It stores the decimal value to something like 13 or 14 places. Now, for us to demonstrate an understanding of the concept, I don't think it's critical that you do that, but for those of you that are curious or concerned about the loss of accuracy, that's one way to overcome this. Now, I will also point out here that the cross multiplication and division technique is good, but the end result will be sine of a, not a by itself. In order to isolate a, we must evaluate the sign inverse at the cross product and division. And it's the combination of this expression that will generate angle A for us. And this appears to be 46.7966 degrees. Now that we have 2 of the 3 angles known, we can subtract from 180 to identify the third. Or we could also set up another form of the law of sines in order to isolate this as well. If we change the 7 to a 3, and recalculate, that'll also give us this final angle measure, 18.2038 degrees. So this problem is now complete. We were able to solve for all side lengths and angle measures. The 3 that were unknown are identified here, and 3 were known at the beginning and allowed us to solve using the law of cosines initially. In example 10, we're going to do the same thing and solve for the unknown components of this triangle, solve the triangle entirely. But you should notice that this is an SSA triangle, which is case number 2, and we call this the ambiguous case. And there might be some discrepancy as to which solution, if any, exists in this particular scenario. Well, keep in mind that a diagram is provided in this case, and most of our diagrams are drawn accurately, or at least characteristically correct. So if we provide a diagram and the diagram satisfies the SSA condition, we can assume that there is a solution, and we can also assume that we're only interested in the solution that satisfies this diagram. There is no need to investigate the secondary or the ambiguous results from the computation. So let's just go ahead and calculate this like normal. I don't think we'll have to worry about the ambiguity in this particular example. So when we build our table of results, it's pretty easy to see that angle B is what we'll solve for first. We have values that are across from one another in terms of C, so we can set up the law of sines to solve for angle B. So using the same setup as before, it appears that angle B is equal to 59.1598 degrees, 59.1598 degrees. And the sum of these 3 angles must be 180, so we know that A is equal to 180 minus 75 minus 59.1598. And that appears to be 45.8402 degrees. And then finally, to obtain side length A, don't get distracted or complacent here. This is not a right triangle, so we cannot use the Pythagorean equation. Instead, you'll have to use the law of sines or the law of cosines, something like that, to solve. Now, we could set up the law of sines, but just to illustrate the ability to transition, I'll go ahead and use the law of cosines this time. And so here's the expression that I had memorized earlier, or you may have it written down on your reference material too, 6.6844. 6.6844 is the result for that side length. And now we've solved the entire triangle. So let's now take a look at the last example in our review here. And this one's one of those extension or challenge problems that I said we might consider on this test. There is some need to recall geometric info or information on polygons from geometry class. And with that, we should be able to generate triangles in intermediate steps and compute the length of this dashed line altogether. So the first thing that I'll remind you of is that there's a rule that states that the exterior angle sum of a polygon, so the sum of all exterior angles, if we measured all of these exterior angles, always adds up to 360 degrees. Now that's particularly helpful for us because in this octagon, an 8-sided figure, we know that the exterior angle of a regular octagon is going to be 45 degrees. So this angle, for example, is 45 degrees. So by extension, it stands to reason that this angle in red is 135 degrees, as is any interior angle of this regular octagon. So I'm going to get that out of the way for just a second and then draw a triangle. If we note this triangle here, and we note that this being a regular octagon has a side length of 1, 1, and 135, then you can certainly use our oblique triangle techniques to find the length of this diagonal, and we'll call that diagonal A. Similarly, you can use side length A along with the side length of our polygon. And if you can determine another angle measure, be careful here though, say this angle measure or one of these, if you can determine one of those, then you too could find the side length, say, of this diagonal B. And with diagonal B or length B known, you could then create a third triangle. With the known information, you ought to be able to solve for this side length, which is ultimately what we're going after in this particular problem. Now that's not the only approach here. In fact, since the octagon has so many sides, there's an interesting result that may occur along the way. Namely, it would be this triangle. To me, it looks like that this angle here is 90 degrees. And before you assume that it's 90 degrees, you should be able to verify whether it's 90 degrees or not. But if it is, and you have the length of your side here, then this length and this length would be the same because they're the same relative component of the octagon. And if this really is a 90-degree angle, then you can switch to the Pythagorean equation to compute your unknown diagonal length. So since this may show up as a challenge question or something similar to it may show up as a challenge or bonus question on the test, I'm not going to complete it in this video, but instead I'll leave you to think about this, and if you'd like any clarifying remarks on it, talk to me in class or send me a message and we can chat about it. This does conclude our third and final review. Hopefully you found them helpful and are well prepared for the test. If you have further questions, please let me know. Thanks for watching.